Alright, pick it back up on standard deviation. All I want to do is go through this one example and then see where we are in time and maybe give you a alternative formula for finding standard deviation, which will actually kind of circumvent the need of doing our subtraction and finding all of these deviations and then finding the deviations squared. So there's another formula, and we'll talk about how it's generated, that will actually allow us to clean these things up, and that's what math is all about. You've talked about this in geometry, that a lot of people think math is all about the calculations, but that's really a small portion of mathematics, where mathematics is understanding the rules, the procedures, the laws that govern it, that actually allow us to avoid calculations, okay, or to minimize them or circumvent them. Okay, so we'll see if we can maybe do a little bit of that here in a little bit. What we're going to do here is try to fill these two data sets in and determine what the standard deviations are of these two data sets. And basically what's going to happen here, what we're doing is saying maybe this data, we talked about, I think an example I gave you, like hair length in the previous video. Maybe this is the hair length of a group of people in, let's say, first period statistics class. And this is then the same hair length information or data, but from 7th period. Okay, and we want to go through and figure out what is the spread of those two data. How do those compare? So as long as we're measuring the same thing, we should be able to do this. Okay, now just debate here, and I cut and pasted these from another textbook. We have to make the argument: are we talking about a sample here, or are we talking about a population? And the way you see here, it's kind of messy. It's kind of messed up, actually. They use X bar, which is it's the sample mean, but then they're divided by n, which might give you the impression that we're doing a population. So let's actually make this n minus 1 here, n minus 1, n minus 1, n minus 1. So we'll say that we've got, 1, 2, 3, 4, 5, 6, 7, 8. Let's say we've randomly sampled 8 people out of first period, and then we randomly sampled 1, 2, 3, 4, 5, 6, 7, 8 out of second period, or 7th period. So what we do, we first have to find our mean. Okay, so all we have to do to find the mean, remember, that's the sum of your data points divided by how many you have. Okay, so in this first one, that mean, I've already done this preliminary work, and you guys can do that on your own, but it's 6. So then what we do is we write down our data points of 4, 8, 5, 12, 3, 9, 5, and 2. And if our mean is 6, I'm not going to write 6 all over again, but we'd fill that column with 6. And now my deviations would be 4 minus 6, 8 minus 6, 5 minus 6, 12 minus 6, 3 minus 6, 9 minus 6, 5 minus 6, and 2 minus 6. Now, if you can do that math, obviously here, you should be able to do that math in your head. You don't need to necessarily write all this down. I think in the next data set, we're going to probably want to write it down. But, 4 minus 6 is negative 2. 8 minus 6 is 2. And that's a perfect example right there why we square our deviations, because those would ultimately just cancel each other out, which is a problem. 5 minus 6 is negative 1. 12 minus 6 is 6. 3 minus 6 is negative 3. 9 minus 6 is 3. 5 minus 6 is negative 1. 2 minus 6 is negative 4. So now I'm going to square those. Okay, so it gives me 4, 4, 1, 36, 9, 9, 1, 16. Okay, so now the sum of those would add all these up. Okay, So that one and that one's going to make 40. That one and that one is going to make 60 total. There's 70. And there's 80. So the sum of my deviation squared would be 80. We're going to divide that by n minus 1. So n minus 1. Remember, n is the number of data points you had. So what do we have? 8 of those. So 80 divided by 7 then. Okay. And I will take a minute to figure out what that is for us. All right, so if we take 80 divided by 7, we get 11.4286. And now we take the square root of that number right there, and it gives you that number, 3.38062, which is our standard deviation then. Okay, and the reason we do that, remember what we did here. If I'm talking about length of hair, this would have been in inches. Our data would have been in inches. And once we did the deviation squared, we would have inches squared as our unit. Well, how would, inches squared is actually a unit for something. It's area. How would I be able to compare an area back to hair length? It doesn't correlate. They're not the same unit. And a lot of times when we do this deviation square, we actually get a unit that doesn't exist. It doesn't make sense. Like especially if you're doing like a mass or something like that, like a gram squared or a pound squared, kilogram squared. Those don't make sense, and we can't then compare the data, okay, to the means. Okay, so there we get our first data set to have that standard deviation. Okay, now what I want you guys to do right now is I want you to pause the video and I want you to construct data set 2 and see what you come up with. Okay, and then hit play again and I'll have all this filled in for us. Okay, so all I did is I listed my data set here. If we average them out, they go to 6.875. And this is where I was saying that you might want to write down, like over here we said 4 minus 6, we wrote it down. Here you might want to actually write down 5 minus 6.875. I didn't, just did these calculations in my head. I subtracted those things out. Okay, so those were my deviations. Now I squared them. Okay, that's kind of where it became time consuming. But once you square all those, write them down. Again, I would use some type of technology that allows me to not have to, essentially type those numbers in and calculate it every single time that I want to add them. Because then the next thing I'm going to have to do is add them all together. And when I add them together, it actually comes out to a pretty nice number, 74.875. I'm going to divide that by n minus 1, so that was 7. And it gives me remember this is called your variance, okay? My variance is in a different unit. This would be, if this was in units, this would be units squared, so I can't compare back to my original data set then. Okay, so I take the square root of that, and it gives me 3.27, and that would be back into units to the first degree. So now it says which data set has the greater standard deviation. Obviously, that's data set 1. Now, they're pretty close. But data set 1 has a greater standard deviation. So what that means to us is that these things graphed, or I don't want to say graphed, but the concentration of these is more spread out than the concentration of these. Okay, that's what we refer to as the standard deviation. It's how compact the data is around the mean. This one is greater. Okay, so it's less compact than what these are. Okay, so the spread is greater here. Now, one thing that happens with the standard deviation is this becomes tedious. Okay, this x minus x bar stuff becomes tedious. So I'm going to show you over here to the side a little bit of those of you that had me for college algebra. We did some of this stuff. There's some, and it's really you see it in algebra 2 as well. So those of you that didn't have me and were did not take a college algebra should be able to follow along with this. But we have our standard deviation, and I'm just going to do this for, let's do this for a population. So I'm going to use sigma because that's the standard deviation for a population. And I'm actually going to do sigma squared. We're just going to do variance first. Okay, and then square rooting will be the only difference between it and finding the standard deviation. If we think about our variance for a population is the sum from I equaling 1 up to n of x minus mu squared. That's exactly what we were doing here. X minus our mean, okay, squared, and then we're going to add all those up, okay. That is our, come up here, that is our numerator for our variance, okay. And I guess, like I said, I'm doing this one, so I'll divide then by n, okay. So divided by n gives me that. Okay. What I want to do is I'm actually going to see, is there a more concise, quicker method for going through this process, and it all boils down to what we can do right there algebraically. Okay. And remembering what that means to us. Okay. I'm going to rewrite this as. I'm just going to rewrite the right-hand side. The sum now of I equals 1 to n. Now remember what x minus mu squared is. X minus mu squared really means x minus mu times x minus mu. Well, we should be able to FOIL that to x squared minus 2 x mu's plus mu squared. So I'm going to write that out. So x squared minus 2x mu plus mu squared. And this is all going to be over n. So but I'm not really going to do anything with this n right now. It's really not going to transform. So at the end, I'll bring it back in. But I don't want to have to just rewrite all over n every single time that I do a new line here. So something that we know about summations, and this is where I was talking about, if you had me for college algebra, if I have the sum of like x plus x squared, something like that, then we can rewrite that as the sum of x plus the sum of x squared. Okay, so the sum of some quantity is equal to the individual sums. Okay, so I'm going to do that over here. I'm going to rewrite this as the sum from I equaling 1 to n of x squared minus then the sum from I equaling 1 to n of 2x mu and then plus the sum from I equaling 1 to n of mu squared. Okay. Now, when we have, and this would all be over n, but like I said, I'm going to kind of skip that right now. When we have the sum of, let's say I have like the sum of, from let's just say I equals 1 to n of, let's just say a constant. Okay, so the rule for that is that it's just what it turns out to be is c times n. That's how that sum is done. Because think about what this means. Let's say I have the sum from I equals 1 to 5. So I have 5 things in my list. And let's say my constant is like 3. Well, then my first term would be 3, because this is the rule that allows me to generate my terms. So my first term would be 3. The summation means add to it the second term, which would be 3. And then the third term would be 3. The fourth term would be 3. The fifth term would be 3. And I'd stop there because I know I go to 5. And that gives me 15. Well, how can I go from using this information here to go straight to 15 without having to write this garbage in the middle? I just multiply those two numbers. I take these two, C and N, or in this case 3 and 5, multiply them together, and I get 15. Okay, so that's one rule that we're going to use here in a moment. Another rule that happens is, like, let's say I have, let's look at like I equals 1. We'll make it a little bit easier. Go to 3, and then say like 2x. Okay, so, or I'm not going to use x. Let's use I. 2i. It doesn't matter, but it tells me, you know, with I is 1, I'm going to have 2 times 1. If I is 2, I'm going to have 2 times 2. And if I is 3, I have 2 times 3. Well, then the argument is, well, what do these all have in common? They all have this 2 in common. So, you know, I can rewrite this as 2 plus 4 plus 6, so I can get 12. Okay, or I could write it as 2, and then if I factor the 2 out, it'd be 1 plus 2 plus 3, which that would be 2 times then 6, which is my 12 as well. But what's that 1? That would be I. That's my second I, and that would be my third I. Okay, as this is progressing. So what we can find out here then is, to get this, I can actually rewrite this as 2, bring the 2 out in front. I equals 1 to 3 of just I. And what that means is I have 2, and then the sum of I equaling 1, and then the index increases at the next term, I would be 2. So then that rule says we put I down, and then the next one would be 3. And doesn't that match to that right there? So what happens? So these are two rules that we're actually going to use up here. Right here, what we find out is this here, I can't do anything with that. Okay, but over here, remember what mu is? Mu is the mean. Mu is my mean, which is a constant. Okay, x is obviously a variable here. So with the variable things, I'm just going to rewrite I equal 1 to n of x squared. Now, mu is a constant, and so is 2. So what I'm going to do is I'm going to bring the minus 2 mu out in front, and then that's going to leave me with the sum from I equaling 1 to n of just x. And now here, remember, mu is a constant, so mu squared is still a constant. Well, what I mean by it's something like this. It's like a 3. Okay? Well, if I want to find the sum of a constant, all I do is I take how many terms I'm going to have times that constant. So this is actually going, this here is going to actually turn into n times mu squared. Okay. Now we're going to have I equals 1 to n of x squared. Now I'm going to look at this thing here, and I see that right there. Okay, and that jogs my memory a little bit about what mu was. If you remember mu, that was the mean. So mu, remember the mean, is I equals 1 to n of x, and we were using like sub I. I don't have to incorporate the sub I, but it's my x terms, my data terms, then divided by how many I had. Well, if I multiply, so if I have this, if that's how I find my mean, if I multiply both sides by n, I get n times mu is equal to now I equals 1 to n of x. This thing right here is that right there. I can replace that with n mu. So that's what I'm going to do. So then I would have minus 2 mu times n mu. So that times the 2 mu is actually going to give me 2 n mu squared. Okay. And then I have my plus n mu squared. Okay. Keep going a little bit. So these are like terms now. Those two things are like terms. So I've got the sum of I being 1 to n of x squared. Now it's going to be minus n mu squared. Okay. Well, what is mu squared? Well, think about what mu was. Mu was this thing here. Okay. So basically what I wanted to do is try to get this back into working with my values of x, my data points. So I'm actually going to, if this is mu, then mu squared would be this. I equals 1 to n of x over n squared. Okay, that's what mu squared would look like. So I rewrite that. I equals 1 to n of x squared minus, okay, so now be n, but now I'm going to replace mu squared with this thing here. So x over n squared. Alright, so we know that if I have like a over b squared, I can rewrite that as a squared over b squared. So that's what I've got it here. Okay, so I'm going to rewrite this as n from I equaling 1 all the way to n of x squared minus n. Now I'm going to rewrite this as the sum from I equals 1 to n of x, so it's my numerator, squared, all over n squared. Okay, so we're almost there. If I multiply this out, we've got an n in the top of this fraction, we've got n squared in the bottom of this fraction, they actually cancel. And this is going to leave me I equaling 1 to n of x squared minus, now we would have the sum from I equals 1 to n of x squared all over n, and then all over then the capital N that I was neglecting previously, that would be my variance. So it'd be sigma squared. Now what's nice about this, and we can kind of debate and talk about, well, was that really necessary for us to go through all that just to get down to still what kind of looks like a messy equation. But if you think about what's going on here, this is now, it's true, and I'm actually going to scroll over here. It's later in your document here. I'm going to come down to here. This is exactly what I had. Okay. Now I was using n because I was doing it for a population, but we can do it for a sample as well. So the n would just change to n minus 1. The mu would have been like x bar instead of or mu, and that's the mean. But what happens is that you recognize that if I want to find the sample standard deviation in this case, I no longer have to know what the mean was. Okay, so that's nice. And what it allows me to do is, instead of finding every one of those deviations, I can just take my samples, square my samples, okay, square my my data points, and then sum those up. And then I can sum my data points and square my sum. And then divide by n minus 1, and I've got my standard deviation. So it's actually, we call it the computation formula, because it allows us to actually do the computations or the calculations a little bit quicker. All of our calculators are I would bet to, if we were to dig into like the structure of Excel or Desmos or GeoGebra, when we type in standard deviation, this is actually probably what's programmed in them, instead of the formula that I gave you yesterday. Now, why do we go through this practice? One, I think it's good to see and practice some of that mathematics that we've learned in the past, but it also, I think, provides insight that I'm going to give you formulas throughout the year, and then there's going to be times where we go through them and we talk about them, like we did here. But there's also going to be times where it's just, they're very messy. Okay, but I want you to understand that there is validation behind them. There is logic behind them. Whether we have time to talk about them or not is another story. But if we understand our college algebra, if we understand our algebra 2, we should be able to do a lot of this stuff. Now, there are some formulas that involve like a greater statistical understanding. Take maybe a calculus approach, maybe even calculus with like a probability approach. So in creating those formulas, maybe we don't have enough skill or ability yet, or even knowledge, but we do have the ability and the knowledge to be able to use them. Okay, so I think that's a good practice to go through. But we can now use that in one of these data sets. So let's just because these were maybe nicer numbers over here, let's see if we can use that formula to come up with the exact same standard deviation. So if I go with, so the formula was that the standard deviation, oh, so standard deviation would have been, so we had the sum of x squared minus then, now it becomes the sum of x squared over n, and we'll divide that by n minus 1. So look what this means, okay? So this means we're going to take our x squareds and sum them first. Okay, so when we look at our x's, if we square those, we get what, 16, 64, 25, 144, 9, 81, 25, and then 4. So we're going to sum those up. So that would be the sum of our x squareds. So this gives me 368 when we do that. Okay. So in my formula right now, this yellow portion is going to be 368 minus then. So now that's the sum of x's. So sum of x's is just going to be the sum of these. So there's 12, 17, 29, 32, 41, 46, 48. Okay, so sum of, so it'd be 48 then squared. And we'll divide that then by n. So n was, what, 8? And then we'll divide that by n minus 1, which would be 7. So I'm going to go to Desmos and type that stuff in. Okay, so you can see here that when I type that stuff in the Desmos, the 368 minus 48 squared, letting obviously you can type in, you can actually evaluate 48 squared and type that in instead if you want to. Divided by n, and then over n minus 1 gives me 11.42857.143, which you can see is really the same thing that I got up here. Let's see if I go 80 divided by 7. You see that 80 divided by 7 using the previous formula got me the same thing. But in generating that 80, I think, and the statistical kind of world thinks that this is a much longer process, especially much longer if we're talking, hundreds or maybe even thousands of data points, which we would never do by hand anyways, but we would program computers to do it. And if I'm programming a computer, I'll just kind of maybe show this with Excel real quick. If I've got my computer program designed to come up with standard deviation, if I'm using the first formula I gave you yesterday, okay, I have to create in my program a line of logic that has my user input the data like they've done here, but then there's going to be a need for my computer program to take this data and subtract from it my mean, so that number. It's going to have to find all of these deviations. Okay, so it's got to do, and now I clicked and dragged, but it's going to have, my computer program is going to have to be programmed to be able to look at this number, look at that number, subtract them, and put it there. Then look at the next data point, subtract the mean, put it there. Okay, I do that. 10. Oh. So I forgot to make this static. Okay, so those are the numbers I want. Okay. Then, so remember that is my difference in my standard deviation, or those are my deviations. Then we got to square those, so then I would have my computer program say, okay, now we got to recall that number, and we'll square it. And then recall this number and square it, and do that all the way through. Okay. Then I'm going to have my computer sum those. My program would have to then say, okay, find this number, that one, that one, that one, add them all together. Give me that number. And then it's going to have to say, okay, well, what was the number of data points we had, and divide by that. Okay, so that's using so that's the 80 that we would have seen here, and then the 7, and we can then have our calculator do everything. Where if I'm doing it using the computational formula, we can have one, we don't even need our calculator to find the mean. Okay, that's not part of it. But all we have to do is tell our calculator, now what we're going to do is we're going to take that value and square it. Take that value, so take all your data points and square them. So that's a minimal amount of computing power. And then we're going to say, okay, we'll sum that. Sum that list, so we'll sum these. Drag it far enough. So sum those. Okay. Then my computer program can be taught to sum these, which were my original data values. Okay. So now I didn't have to do any subtract. All I had to do is program my computer or my program to square my entries, square my data entries, and to sum my data entries. There was no need for differences and all that kind of stuff that we had to do up here. So I'm able to actually minimize the amount of RAM that my computer uses to generate these values. So you guys have all done this on your TI 384. When you type something in on your TI 384 that is kind of messy or long or a difficult technique, that our calculator, like let's just say I go second calc, let's just say I want to go to 4 here. Like we've all done this, and then when I hit enter, you see you could kind of see it at a moment that it was thinking. We had this little line here, and that just means my calculator is thinking. It's going through the calculations. It's using the RAM, the available RAM, and sometimes that takes forever. Okay, but then it eventually spits the calculation out to us. That means that the calculator for that process was maybe it was the only way it was able to be done, but it was such a hard calculation, so much RAM being used, it just slows or degrades the efficiency of the program. Where if I can better fine tune my formulas, then I don't have to use so much RAM, and the performance and the efficiency of the program can be quicker, which in the whole grand scheme of things is we can save time, which time is money, so we ultimately save money by making our programs more efficient, and our users don't have to wait for it to process. So those are reasons why maybe we have multiple formulas for the same approach, same problem. As we go through, and I ask you to do things by hand, I don't care which formula you use, whichever one makes most sense to you. A lot of people will probably use this first one because it's the first one introduced. But like I said, I think the second one is more efficient. It's easier. You don't have to find the mean, which is nice. But I'll leave it to you.